Okay, so good morning, students. Today we will be coding Word2Vec negative sampling, which is a method that is much more efficient than the traditional skipgram one, right? So today we will be using a lot of the code from the first video. So if you haven't watched that one, please go back. And so we will be doing some low data, which will be mostly similar. And then we'll be doing preparing train data. And this one will be also very similar to the last one. There will be two primary sections that we have to code a lot. That is negative sampling, which the paper has written a formula in which how do we create the distribution in which we draw the sample, right? So we're going to code this to create understanding what does this actually mean. And then we're going to actually write this model together, which will be, I don't think it's too difficult, but there will be some work that we need to be done. And then there will be some training and of course, plotting the embeddings and some cosine similarities, all right? Which will be mostly the code we have coded last time. All right, so without further ado, then why not we clear all the outputs, restart our kernels, make sure everything is clean, and let us run all this to remind us what we have done. And we can open the load data. So in the load data, this is the only one line that I have changed by adding some more terms, which will be useful for us to understand the distribution later on. So we're going to run this, right? This is Word2Index, adding Unc and index to Word. All right. So now, once we finish this, so we can close this. And prepared training data is basically the same, which is mainly the function of the random batch. We run through each of the corpus and we run through each of the word from the second word and to the second last word, and then making a pass of center word and the outside word, and then we just randomly draw according to the batch size. All right, so that is the prepared training data. Now the next thing, the first thing we have to code now is negative sampling, right? Which the papers say that, hey, of course, the question is how much we need to draw, like in how do we draw the negative samples, right? Of course, the idea is that we can use UW only. What is UW? UW is basically the frequency, right? So if this word appears a lot in the corpus, then maybe we can draw it more frequently. But of course, the idea that sometimes a lower term frequency is also a very good negative, right? So maybe we can tone it down by this exponents. And then we're going to scale this by z, which is just turning the scale to 0.001, right? Mostly the numbers just scaled the digits. We're going to understand this much more once we code this. All right. So firstly, we're going to set the z to be z equals 0.01, which is used in the paper. And then to calculate the UW, we have to firstly count and then also get the total number of words, right? Then we can divide both of this to get UW. To do this, we're going to just simply do from collections, import counter, a very nice function, the word count, equal to counter, flatten, office. Right, so it's nicely count everything for me. And then what I can do is now I can count the total number of words, right? And to do that, what we're going to do is we can say for W and Z and word count dot items. And we're going to get only the Z. And we're going to treat this as a list and then apply a sum function. This will be now the total number of words. This is a little bit wordy, so let us change to total words. Right. So now we have the word count, and we also have num total words. Then I think we are ready to calculate UW. So for UW, what we're going to do is we're going to do unigram table, which going to hold the probabilities in which we draw some words. And then we're going to say for V in vocabs. What is vocabs? So these are the vocabs. For each of the word in the vocab, we're going to first calculate UW. And before I actually code this, why not I just copy this one to here so that we can know what we're actually coding. So UW is basically for each of the words, right? So we're going to say word count B divided by num total words. Right? Actually, we can try to print this, right? And we can say that this is a very nice frequency, and then we can do UW equal to UW 0.75. Then you can see that the numbers are scaled in such a way that maybe let us try. This is maybe alpha, and then we can rate VW alpha, so we can check how does it differ, right? So this is basically okay, this looks very difficult, right? So I'm gonna do okay. Oh, great. So now I don't think we can do that, right? Because this is each of the word, but we don't need to. Actually, what we're going to do is we can do like this. All right. So you can see that by multiplying this number, then the cat is got up the probability, all right? But similar to the grapes, right? The grapes also got add up the probability, right? So in such a way that there's also a better chance, right, to get this lower terms. And then of course, so we can divide it by Z, right? Now we can clearly see how does it look, right? So now from this number, it becomes 2110 simply because this is divided by 0.001, right? But now you can go to fish. Now fish has a much higher probability, right? 92 compared to 210. So there's still a lot of chance that fish is going to be picked, right? Rather than this number, which is actually very, very small compared to this one, all right? So I think that is how this one works. And then what we're going to do is we just say unigram table dot extend V times UW alpha. And now we're going to have a very nice unigram table. Sorry, I forgot that this must be in. Yeah, actually, if you look at the function, there's an int here in the paper. Yep. Because it should be a definite counters, right? So now, so you can see that now we have a very nice, basically this unigram table is like V. So how many cat? 210 cat, because I multiply with this UW alpha, right? So I have that many of cat. So when I do the counter, I can actually count that many cat, right? But when I actually random.choice, I'm just gonna random.choice this one, right? Because this is just a a list of things, right? And there's a like 200 out of all this chance to get cat, and fish 92 out of all this number add up together to get fish, right? Great. So that is the unigram table. All right. I think it's very straightforward. So once we finish that, we can now close this one. Now let us try to work on the model, right? So the model is according to this function, right, in which we want to maximize this one, right, the probability of this one. And we just apply sigmoid to turn this into 0 and 1. At the same time, we want to minimize this one, right? That's why we put a negative here. And because this is a negative minimization problem, we just turn a maximization problem into a minimization problem by putting a minus in front, right? So that is very obvious. Now we can, this is basically what we have already created last time, which is basically inserting in sequence and then turn everything into a tensor. All right, so now we can create this function that can draw negative samples, right? So to do this, we have to firstly know what are the targets, so we don't draw any samples that are equal to targets. And then we need to have the unigram table and how many negative samples, and we're going to use that as K. All right. And so firstly, we will get the batch size. The batch size will be useful because we want batch size number of negative samples, of K samples, right? So basically what we want to return is something like batch size K samples of that batch size. And then of course we want to return this one, negative samples. So now what we're going to do is for each of the batch, we're going to create basically we want to create 1, K samples like this. Yep. And then if we have 2 batch size, then this is going to be 2, right? And then that will be fit to here. So now what we can do is firstly get the target index, which is targets of that batch, of that item. But the reason why we need to use item is because simply because this is a tensor for sure. And then n sample, this is to keep this one. And then we're going to say that as long as the length of n sample is less than K, right? Then we keep finding. And if the so the negative sample is basically random.choice and unigram table. And of course, if this negative is equal to target index, right, then it's no go, right? But we have to make sure this is Word2 index. We're going to use continue. If it's not, then it will continue coming back to here and random.choice again. And then we're going to simply append this one to the negative. Finally, once we have all this, we're going to add this to this guy, all right, so that it becomes this batch size, K. So now right here is negative samples. Dot append. Prepare sequence, right? So turn everything into tensor and sample, Word2 index. Dot reshape 1 minus 1, right? So now we have this 1, K nicely. If we don't reshape, then it will be K, and we cannot stack to make it this shape. And of course, finally, once we have everything, we can do torch.cat, negative samples to get this batch size, K. All right. So I think this is I think this is a very nice exercise for you to practice your Python skill. So why not we just try this to make sure things look nice. So we're gonna say batch size equal to 2 and xy equal to random batch and size and purpose. And what we're going to do is x tensor equal to long tensor x tensor equal to torch.long tensor. All right. So now once we have this y, we can now say that k equal to 5 and say negative samples is equal to negative sampling, and that gets us y tensor and unigram table, and k is that, right? And now we can actually print this negative samples. And this is exactly 2,5, right? Of course, we can print 0, so 3, 4, 6, 1, 2, and we can actually print y tensor 0, and this is 7, right? So there are no, all the negative samples is not belonging to that. We can also check the second batch, right? And you can see that these are all not belonging to 1, right? All right, great. So I think that is a very nice thing we have done here. And once we have this negative function, now I think we can actually create this model. All right. But please give me 1 second to take some drinks first. All right. So now we can actually write our program, and we're going to say class skipgram, but belonging to the negative function, negative sampling. And we're going to inherit from NN module. There are 2 functions we need to always create, that is init and also the forward function. Yep. If you have watched my video last time, then this won't be actually too much different, right? So we can code this like this. So can we say skipgram negative comma self dot net. All right. Which will inherit everything from NN module, and then we're gonna say self.embedding for the center word is NN.embedding. Sorry, vocab size and embed size, and this will be specified like here. Similarly, we're gonna do this for outside word, and I think we don't need anymore, right? And then one more module we're gonna have is log sigmoid, which is basically equal to nn.log sigmoid. We need this because the equations are right here require this sigmoid here, log sigmoid. Yep. Actually, why not? I just copy this function nearby to me so that I can refer to it. So now we have all the layers we need. So now we can perform this forward function. And so we have this center, outside, and negative words, right? This time is not all over caps because that would takes too much computational power. So the center word and the outside word is both basically batch size, 1. And for negative words is basically batch size, comma K. Right. All right. So now what we're going to do is a center embed equal to cell.embedding center. All right. And this one is basically batch size, comma embed size. And we're going to do this all for it. So this one will be outside. And this one will be basically, oops. This one will be basically their negative word, right? So we're going to say, oh, I think I choose again wrongly. Give me 1 second. Okay. And this will be negative, right? Embed. Actually, I forgot one thing, right? Because for the negative, we just use the outside word embeddings according to the equations. Yep. So now we just change this back. So sorry. This one and this one is negative words. Why not I just use it negative, right? Because it's going to be very long. And this one is K. All right, so now we have a very nice thing here. So we have to do here, right? UOVZ. So the UOVZ is basically nothing but outside embed dot BMM center embed dot transpose 1,2 and this is basically very similar to previous one, and then we squeeze the second dimension. Now this one is simply batch size, comma 1, and then once we do that, we need to do this UKVZ right here. So okay, make this smaller so you guys can see. So UKVZ is basically minus, right? We have a minus sign, negative embed dot BMM center embed dot transpose 1,2. All right, and then we're gonna similarly squeeze this. And put this batch size, comma 1. And then no, this is probably batch size, comma K, right? Because this one is batch size, comma K, and this one is embed size, comma 1, right? So the K will remain. Now what we're gonna do now is basically sum. We still have this sum function, right? So we're gonna do UKVC sum, which is simply torch.sum UKVC, and we're gonna sum up. So sorry, we're gonna sum. Okay, where am I? We're gonna sum at the for across K, right, which is the second dimension, which is this one, right? So this dimension is 1. So we're going to sum across that. And then finally, we're going to reshape this to minus 1, 1, which is batch size, comma 1. All right. Now, finally, the loss function is nothing but self.log sigmoid UOVZ. And plus self.log sigmoid UKVZ sum. All right, so that would be the log sigmoid part, right? But we still have this minus, right? So we're gonna just put this minus right here. Return minus torch.mean loss, right? again, why do we need to have a mean? Because this across a lot of batches, so you have to mean and get one number, otherwise you cannot backpropagate, right? All right, so now I think it should be good. Okay, if I don't do any bad mistakes. So always test your model, right, before running the training, which is costly. So right here, I think I already have X tensor. Yep. And I also have Y tensor, right? Yep. So I think we just simply embed size equal to 2, vocab size equal to length of vocabs. And then we just call this right away. Model equal to skip gram negative vocab size and embed size. All right. And of course, we have to also, if we want to, so we just create the model, right? But to run this model, actually, we need 3 things: the center word, the outside word, and the negative words, right? So we can get some negative samples that we have already created earlier. So we can do this. Loss equal to model X tensor. This is a center word, and this is the outside word, and then this is the negative samples, right? And now we got a very nice loss. Great. So if this run nicely, then it means we are doing everything correctly. Oh, lucky me, right? So yep, I think this part is fairly difficult. If you're not familiar with Python, it can be easily confused. So I recommend you do this step by step, and then try to monitor the shape and print them one by one, and get the intuition how it works. All right, so now I think the model is okay, and the last part we have to do is actually the training. So we're gonna do vocab size equal to actually we already have all this numbers, so we're not gonna need that. We just need to create the optimizer optim.thumb, the parameters, right? And LR equal to 0.001, 0.01, right? Yep. For those who are new to neural network, this is the learning rate. So yeah, this is a number. If your loss is not decreasing, is good practice to just make this smaller. Sometimes you're making too big step. So now right here, we're going to do num epochs equal to 5,000. And for epoch equal to range. This is basically the same as what we have done in the last section, right? In fact, why not I just go to what we have coded earlier right here, and just copy this right here. So this is going to save us a lot of time. Right? So we're going to copy this, right? And but we have to change one part, right? Obviously, is this negative sampling, right? So whenever we send to the model, we have to say that negative samples is basically equal to negative sampling, and then you input the label tensor, right? And specify the k, right? In which we already have the k, which is the 5. And when we put this here for every batch, right? So that it works nicely. And I guess that should be it. And let's try to run this. And missing one require. Okay, so I think I still need the unigram table. And come on here, and then this should run. Okay, great. So it seems like my loss is going down, and the loss is getting lower, which is good sign. All right, so I think that is a very quick training. I'm just simply using the same old code that I use. Now let us plot the embeddings, right? So right here, I guess we're gonna do the same, right? So we can try vocabs, and this is last time I just tried to demonstrate how we can calculate embedding for one word, which is basically averaging across the center word and the outside word. And right here, this is just a function, and we can check for each of them. But for handiness, we just loop through all the vocabs and just write them. And you can see that I think we run nicely, and all the fruit things are right here, and all the like fish and cat is right here. Fish is not so much work, does not work that much because it's only up here once, right? And then by the way, for those who cannot code this quickly, you just simply use the code of the previous tutorial. And on the cosine similarity, last time we also demonstrate that we can simply dot product like this, and we can get a number, right? But formally, just something that I did not do last time is basically divided by the norm, multiplied together, right? So this is the right function of the cosine similarities. By normalizing according to the norm, then your number will be correctly normalized. So we can try maybe maybe cat, right? We don't have actually cat, right? We have banana, fruit, and maybe cat. Right. Right. So you can see that banana and cat is a much smaller number compared to banana and fruit, which is a very, very close number together. All right. And I guess I'm going to change this one to make sure there's no errors. Okay. So I think that is Word2Vec negative sampling, right? For those who want to take a look at my code, just go to GitHub and go to fundamental code along 0 to Word2Vec sampling, right? And then you should get the file. All right. Thank you very much.